In this work, we present an autonomous navigation in retinal microsurgery and provide evaluation in ex vivo porcine eyes. Retinal microsurgery is one of the most challenging surgical procedures due to its high precision requirements, limited workspace, and the delicate tissues involved. In most cases, an operating microscope is used to obtain a top-down view of the surgery scene. The surgeon must insert a surgical tube and light source into the eye to operate on the retinal tissue. One challenge of retinal microsurgery is limited depth perception due to a constrained top-down view. With a microscope providing this view, it can be difficult to determine the distance between the tool tip and the target on the retina. However, as the surgeon moves the tool closer to the target, they will observe the shadow of the tool shaft, and tool shaft itself will converge to a point. This convergence indicates that the tool tip is near the target on the retina. Therefore, we consider the shadow to be a valuable cue for estimating depth during retinal microsurgery. So in this work, we propose an improved autonomous navigation process. Our workflow begins with the user selecting the desired target by clicking on the screen. Next, we input this location into our network and output a distance vector. We predict multiple points near the target point and use these points to fit a local area around the goal. We use optimal control method to generate a trajectory towards the goal position. By incorporating the chance constraint into the cost function, we can ensure that the likelihood of collision with the retinal surface remains below a set confidence level of 1%. This approach offers the advantage of increased safety during the navigation process. We collect data, train our models, and test our algorithms using different eye models, including open sky and intact pig eyes. Here is our experimental setup. For intact eye experiments, we use a vitrectomy machine to remove the lens and a portion of features inside the eye. We have determined that this approach enhances camera visibility compared to using eyes without any removal. We collect our training data manually for pig eye experiments. For open sky eye experiments, 1,800 trajectories are collected for 12 eyes. Further details are provided on the right. Collecting intact eye data presents a challenge, as we require the use of very fresh eyes. The cornea gradually becomes blurry over time, and only a clear cornea can provide a clear top-down camera view. To train our network, we use the same hyperparameters as in our previous work, which are shown in this slide. We implement the RCM constraint to minimize the scalar force applied to the scalar insertion point by the surgical tool. This is crucial, as any force applied to this point has the potential to damage the eye. To achieve this, we include equation 3 in our cost function to minimize the red dashed line. When the value of this line is 0, we are confident that the tool is oriented as desired. The results for network training indicate a clear trend, with smaller prediction errors observed when the tool is positioned closer to the retina. The trend remains evident for intact eye training. The experimental results are shown in the table. We navigate to 20 predefined goal positions for both open sky and intact eye experiments, and compare the performance with and without chance constraint and MPC. The white points are the predefined goal positions, and the green points are the actual landing positions. The red boxes show that using chance constraint method and MPC helps to lower the probability of collision between the tool tip and the retina, resulting in improved safety. When comparing navigation without and with the use of MPC, we observe a significant reduction in the mean time duration, with a decrease from 36 seconds to 7 seconds. Our algorithm allows for the possibility of changing the target during the navigation process and can accurately update the goal to reach the new target. To simulate head drift, we randomly move the eye along XY axis for a small distance and use optical flow to update the goal and RCM point. Our workflow is robust enough to reach the updated goal as shown in the video. To demonstrate the effectiveness of the RCM constraint, we use a surgical tool with integrated FVG sensors to measure the scalar force. As shown on the right, this tool can measure scalar force along XY axis during the navigation process. The results show that all measured forces never exceed 60 newtons for all experiments. In this work, we test our improved robotic system using both OpenSky and intact pig eyes. The results demonstrate less than 60 microns mean XY axis errors. Moreover, by using chance-constrained incorporated MPC, a safer, faster, and more accurate navigation process is obtained. We also demonstrate that our system is sufficiently robust to track the updated goal accurately during head-drift simulations. Future work will focus on experiments that use intact pig eyes for subretinal injection. Also, this work was supported by NIH and partially by JHU internal funds. Thank you for watching.